Section 9.5 is hypothesis test for a standard deviation. Remember when we did the confidence intervals for standard deviation, we used a chi-square distribution. The chi-square distribution uses a table to look up critical values, just like it did when we went over confidence intervals for standard deviations and variances. We're going to have to use the same thing for this. There's only two objectives. The first objective is to find critical values of the chi-square distribution. This part should be reviewed since we've done this in Chapter 8. I believe it was Section 8.4. Remember, the chi-square distribution starts at 0 and it has only positive values. So if you get a critical value for a chi-square distribution, you know it's going to be positive. Also, that distribution changes as our degrees of freedom change, and it's no longer a symmetric and unimodal distribution. It is a skewed right distribution. Those are the two important characteristics. Also, the chi-square distribution uses the area to the right whenever you're finding critical values. This is different from the t-distribution and the normal distribution. The t and normal distribution use the area to the left, but the chi-square distribution uses the area to the right whenever you're finding critical values. In this first example problem, we're asked to find the critical value chi-square 0.05 for a chi-square distribution with 10 degrees of freedom. Before I do that, I want to make another note here. If I want this area for the shaded region, let's say that this area right here was alpha, this chi-square, we would use the area 1 minus alpha. This critical value is on the left, and this critical value is on the right. Because the chi-square distribution starts at 0 and gets bigger, the number or the critical value for the right will be larger than the critical value for the left. Does that make sense? That when I say chi-square left and chi-square right, this is what I'm talking about, where the chi-square for the left-hand side of the graph uses 1 minus alpha for the area, and the chi-square on the right just uses alpha. This is different from the t-distribution or the normal distribution where we use the area to the left. Here, if this area is alpha, this critical value would just be z sub alpha. But if this area over here were alpha, this critical value would be z. We call that 1 minus alpha when we did the inverse norm. So you see how the t and the normal distributions, since they both use the area to the left, if I'm finding a critical value on the left, I just use the area that I'm given for alpha. But on the chi-square, it switches. If I'm finding the critical value for the right-hand side, I use the alpha there for the right, but then I do the 1 minus alpha for the left. It's complete opposite. So in this problem, we're asked to find the critical value chi-square 0.05 for a chi-square distribution with 10 degrees of freedom. So our alpha level here would be 5%, and this would actually be the area on the right since we're just using alpha. This area is alpha, and we're looking for this chi-square that would be the area to the right. Since we're told we have 10 degrees of freedoms, once we get our chi-square table, we go down the column for the degrees of freedom and see 10, and then we go across the table until we see where the area is 0.05, and that means that this critical value would be equal to 18.307 for a chi-square distribution with 10 degrees of freedom. That's what this number would be right here. Objective 2 is to test hypotheses about the standard deviation of a normal distribution. The test statistic for the hypothesis test, whenever we want to test a claim about the standard deviation, is this number right here. This is our test statistic. We don't have a function on our calculator that's called a chi-square test. We have to use this formula in order to get our test statistic. In this formula, n is equal to the sample size, s is the sample standard deviation, and sigma sub naught is the standard deviation from the null hypothesis. These are the values that you need to know in order to calculate this test statistic. Now remember, anytime we're working with a chi-square distribution, you have to make sure that your samples are drawn from a normal distribution. You will need to be told this or have some way to tell that your population standard deviation is normally distributed. If you're doing your own research in the future, that's one thing that you definitely need to check. This is very important. Once you calculate your test statistic, you're then going to compare your test statistic value to your critical value. These are the steps you'll go through whenever you perform a test of hypotheses on standard deviations. When we were testing claims about means and proportions, we had 6 steps, didn't we? The one step that's missing here is to draw a graph. You don't have to draw the graph, and on your test I didn't ask you to draw the graph, but I'm going to show you how it looks if we did draw the graph to explain step 4. So your first step is going to state the null and the alternative hypothesis. That's the same as it was before. Then you want to choose your alpha level. You'll be told what your alpha level is, and if you're not told, assume it's 0.05. That's our default go-to alpha level. Then you have to find your critical value. If you have a left-tailed test, your alpha level is going to be on the left. This area right here would be alpha, and this critical value would be found by using 1 minus alpha for the area. This is your left critical value. That's why we have the 1 minus alpha right here. For a right-tailed test, remember the chi-square distribution uses the area to the right, so if this area is alpha, this critical value would be chi-square alpha. And then for a two-tailed test, you would have two critical values, and we take our alpha level and we split it evenly over these two tails, so this area would be alpha over 2 and this area would be alpha over 2. To get the critical value to the right, you do chi-square alpha over 2, and to get the critical value on the left, you would use chi-square 1 minus alpha over 2 for your area. I think the pictures do a better job of explaining things than just looking at these words and symbols. Do you agree? Then you want to compute the test statistic. Once you write your null and alternative hypothesis, you're going to have numbers for all of these things, all of the variables here. This number right here is the one that comes from your null hypothesis. You'll know the sample size and your sample standard deviation from the information that's given to you in the problem. So you calculate a number for your test statistic. Then you have to determine whether you're going to reject the null hypothesis or fail to reject the null hypothesis. This to me looks complicated. By the way, the chi-square here is your test statistic. These numbers here are your critical values. And this is your test statistic and your critical value. Now let me explain it with pictures. For a left-tailed test, we would reject the null hypothesis if our test statistic is less than this number right here, this critical value. Well, on a left-tailed test, we reject if my test statistic fell in the red region, the critical region, wouldn't we? That's the only time we reject a null hypothesis, is if your test statistic falls over here. If your test statistic is greater than chi-square, you would fail to reject the null hypothesis because your test statistic is to the right of that critical value. This you may have trouble interpreting and getting sense out of it, but I think the picture here speaks volumes. If our test statistic fell in this region right here, we would reject the null hypothesis. If it fell over here, we would fail to reject the null hypothesis. If you have a right-tailed test, we would reject the null hypothesis if our test statistic was bigger than our critical value. Well, that makes sense. Here's our critical value, and if your test statistic is bigger than that, then you would reject. And when I say reject, I mean reject the null hypothesis. On a two-tailed test, if your test statistic is bigger than the critical value on the right or smaller than the critical value on the left, then you would reject the test statistic. This is bigger than the critical value on the right or smaller than the critical value on the left. So if your test statistic chi-square falls in the critical or the red region, then you reject your null hypothesis. Otherwise, you would fail to reject the null hypothesis. We just have one example problem for this section. It says, to check the reliability of a scale in a butcher shop, a test weight known to weigh exactly 400 grams was weighed 16 times. For the scale to be considered reliable, the standard deviation of repeated measurements must be less than 1 gram. The standard deviation of the 16 measured weights was S equals 0.8. S equals 0.8 is our sample standard deviation. Oh, by the way, N was equal to 16 because we weighed this weight 16 times. Assume that the measured weights are independent and follow a normal distribution. You need this assumption in order to be able to use the chi-square test. Here's the last and most important statement, because you'll be able to write your null hypothesis and state your conclusion all from this last sentence. Can we conclude that the population standard deviation of the measurements is less than 1 gram? That's what we want to answer. We use this information to write our null and alternative hypotheses. Remember, when you're writing hypotheses, you need a parameter and a number. What parameter are we testing? Mean, proportion, or standard deviation? And what variable do we use to represent the population standard deviation? Sigma. The null hypothesis, does it contain equality or an inequality? And then what number do we use? 1. And that's from that 1 gram right there. Can we conclude that the population standard deviation of the measurements is less than 1 gram? So what will our alternative hypothesis be? Sigma is less than 1. Do you see how all of that information I was able to deduce from just this one question? What will our alpha level be? And then you weren't asked to do it, but I'm going to do it. I'm going to draw the picture because I think the picture makes life easier. We draw a chi-squared distribution, and that's just a distribution that's skewed right. Will this be a left tail, right tail, or two-tail test? Left tail, and what do we look at to determine what tail it's going to be? The alternative hypothesis. So this is pointing to the left, it's going to be a left-tailed test. That means that our critical value is going to be on the left. And all of our alpha is going to be in this red shaded region, and I need to find the value of this critical value, and how I find it is by looking it up on a table using 1 minus 0.05 for my area. So what I'm going to call that is chi-squared 0.95, because 1 minus 0.05 is 0.95. Our sample size is 16. What will our degrees of freedom be? 15 with an area of 0.95. Now, this is where I said you're going to have to print the table out of the ebook. Earlier, I went ahead and pulled it up. This is from your ebook. You go to the appendix, and it's table A4. Our degrees of freedom are 15, so that means I'm using this row right here. I can't write on this because I'm not in OneNote, but we use this bottom row, and our area we said was 0.95, so I go down the column with 0.95, and there's my critical value, 7.261. Now the next thing we have to do is we have to calculate our test statistic. Whenever you calculate your test statistic, start with the formula for the test statistic. Then just drop in the numbers from the problem. What number am I going to plug in for n? -1. What number do I plug in for s? 0.8. And then I square that, divided by, and what number goes in the denominator? 1. It's the number from your null hypothesis. So that number was 1 squared, and 1 squared is 1. So now we go to our calculator. 16 minus 1 is equal to 15 times 0.64, because 0.8 squared is 0.64, and you divide that by 1, it's just that. So what is this going to be? So that means that our test statistic is chi-square equals 9.6. If I were to plot this number on the graph, would it be to the left of 7.261 or to the right? It would be to the right. So our test statistic falls right here, 9.6, which means that what's my conclusion going to be? Not my conclusion, my decision. Reject or fail to reject. We fail to reject the null hypothesis, and you can use my shorthand. F2R means fail to reject. And then we write our conclusion. Because we failed to reject the null, we did not prove the alternative. The alternative was that the population standard deviation is less than 1 gram. I failed to prove that, so I have to say we cannot conclude that the population standard deviation of the measurements is less than 1 gram. Does it make sense why we can't conclude that the population standard deviation is less than 1 gram? The population standard deviation being less than 1 gram is our alternative hypothesis. We failed to reject the null, so we can't say this. And this wraps up section 9.5.